On this slide, we're going to have a look at verifying poorly performing or bad SQL. Okay, is it really the real problem or something else on the system itself? And lo and behold, I have experienced this myself earlier on, okay, with a number of systems. So we always need data. We need data collected at the operating system to do this. What we want to confirm that it really actually is the database that is having a problem, and within the database it's SQL statement. So we need to collect data. There are a number of tools. Oracle has a tool called OSW, which is a short form for OS Watcher, which is a tool we wrote a while ago to allow the DBAs to collect data on a particular operating system that is running an Oracle database. It just uses the standard tools to collect the operating system information. This little tool was tailored per operating system where the Oracle database actually runs. Also, the built-in little data warehouse for performance data, the AWR, Automatic Workload Repository, Advanced Workload Repository, actually has certain aspects of database performance data out in it. And we can use the information in there also. So what we want to do is have a look at the system. Are we experiencing a resource shortage? And the resources that an operating system supplies to a program, and a database is nothing more than a sophisticated C program, is CPU, memory, and I/O. In particular, we're interested in CPU because a lot of times SQL tuning issues manifest themselves on the operating system as high CPU time. So are we short of resources? And one of the resources they mention up here that we don't spend a lot of time looking at is parallel execution slaves. In this course, we're going to focus on serial execution, but it gets mentioned here, so I just thought I'd mention it. Okay. Now, are we short of resource? If we're not, okay, we've got lots of CPU, memory, and I/O on the system, and we're not saturating them, and we have some general guidelines that are written per operating system, but for Linux that we actually run the course on, we believe that generally you shouldn't push the CPU, I/O, and memory beyond 95%. If you do, then the operating system starts reacting to that, and it tends to lead to a decrease in performance and that. And if one of the problems we end up with is we have high CPU utilization that we've determined from the data we collected at the operating system level, then next question we want to ask is which processes are using that resource, okay? And what we're trying to determine is that the database processes, that means we could have a performance issue with a particular database, or is it something outside of the database? And that's the aspect I've actually ran into myself. Sometimes we have other things running on the operating system that aren't supposed to take much resources, but suddenly they've got 95% of the CPU and 88% of the memory. And suddenly they're a big consumer resources. In that case, maybe we need to get that thing off of the database servers somewhere else, okay? But if we have high CPU, and it turns out to be the Oracle processes, and it's relatively easy to check with a PS command if they belong to Oracle. Every process is documented at the operating system with the system ID of the database that we're running. So if this is the ORCL database, it will have ORCL. In our case, we're using a database in the practices and for the demos called systune. It will have systune as the name of the database. So if it turns out to be an Oracle process, then we need to find out why they're using the resources, and maybe the problem is for those processes, it's a problem with the SQL statement. If there isn't a problem with the CPU and we go down the other side of the diagram, we may need to collect some additional data. Is it a problem with the system overall running something else that we can determine from the operating system stats? Is it a particular database instance that is behaving slowly? Maybe in that case, we might want to have the DBAs do a general tuning exercise at it also as part of this process. Is it a set of slow sessions, one or more slow sessions? Then we could collect additional information for that session to see why it's slow, but we determined it wasn't the CPU that was a problem, it was something else. But either way, if we determined high CPU on the Oracle processes or a slow session, slow instance, we need additional information. Collecting the basic trace information for the SQL performance may lead us to a better understanding. So we can collect the 1046 trace by turning on the trace events, and we'll look at a whole group of ways of doing that in an upcoming chapter. And then we can run it through TK-Prof to get it formatted in a little more human readable form than the raw trace file. And then we can make a look at it and we can discover different things. There can be expensive SQL that needs to be tuned, or we could discover it's not the Oracle database. There could be lots of wait time in the middle tier, and we can actually identify that as an issue. Where is the time being spent? Is it being spent in the database, or is it being spent at the operating system somewhere else, such as a middle tier or from a client tool? You can always run into an Oracle bug with the Oracle software. The software is not perfect. We make it as good as we can, but we may have to eventually work with the DBAs to have a bug logged if we can't solve the problem. And you can log performance tuning issues as bugs to get Oracle support's help. If you've exhausted all the things that we suggest on this course, that may be a good course to work with the DBAs and get an SR, a service request, logged in My Oracle Support. There are a very limited number of people in an organization that can officially log SRs. Everybody, the DBAs and all the developers should have read access to My Oracle Support. A few will be able to log calls. Or is it a misconfigured application? Okay, and if it's SQL statements that need to be tuned, then we might want to pick a tuning strategy. All we've determined where the problem is right now. How limited or how broad scope, we can limit it down to a group of SQL statements that are taking either longer in wait time or longer in CPU time than we would like to execute. Then maybe we can do a SQL tuning exercise on it. The next session is looking at the tuning strategies. We're going to have a look at some sanity checks, some quick checks we should make. Talk about if the quick checks don't lead us and we can't find a better execution plan easily, then maybe we need to do an advanced tuning analysis. Okay, and then we'll have a look at a parse reduction strategy, a simple way of if we can find a plan where we like the performance better, can we get it to use the plan as a quick solution? Or can we figure out how to get the optimizer to use that plan? And if we can't find this quick solution, then maybe we need to do a detailed, more exhaustive analysis on the problem. Or if we're really just determined to find what the underlying cause instead of a quick solution. So, tuning strategies, we have some basic checks we should do before we try to decide whether we're going to do an advanced tuning or a simple. If this leads us to a solution, then we solved it fairly quickly. We could decide to do an advanced SQL tuning analysis. We're going to need more details, information. There are times that it's not the execute time that is causing the problem, it's the parse time. And we'll look at some parse time reduction strategies. Ability to compare plans is a basic strategy for doing SQL tuning. If I can find a better plan or a time when it used a different plan in the past that we like the performance better, maybe we can get the optimizer to do it now. If all else fails, we can go in and have a look at the detailed analysis. Okay? And to do the detailed analysis, we need a much broader understanding of how the optimizer works than we need for doing a quick tuning exercise. So when we get into that, we'll get you into looking at more details of the optimizer. So first off, we should always check the basics. And these are things we should check every time we contemplate doing a tuning, SQL tuning exercise on the database. Are the statistics being collected and up to date, and are they appropriate for the database? Another problem that can be very difficult for DBAs and Oracle support to debug, they can actually waste days, if not longer, on it, okay, is making sure that we have reasonable initialization parameters. There are a group of 36 basic parameters that we suspect that typical databases only need a dozen to 2 dozen set. There are over 300 parameters overall for the database. The majority of them don't need to be set, and they really shouldn't be set. There are a lot of cases they were set to a particular value of the advanced parameters. In an earlier version, perhaps 7.3 or 8i, to solve a particular problem with Oracle, there was a bug. By doing something a certain way, tuning the database a certain way, we avoided that bug. They should have been taken out as soon as the database no longer had the problem. Invariably, they quite often get lifted in there. By the time we're on 12c, they're actually badly mistuning the database. They're causing us to have it badly tuned. And without realizing its poor parameters initially, DBAs and support can spend hours or days looking at this area, only to discover it's an inappropriate set parameter. So now we encourage the DBAs, every time they upgrade to a new version, test the database with only the basic parameters set to try to avoid. But once again, it's good to ask the question. And for most developers, you may not have any elevated privileges on the production database. You may need to ask the DBAs to check this for you, unfortunately, but that's the nature of the beast. If you've got your own test or development machine, you may have some privileges and may be able to do it in that case. Also make sure the optimizer is running in proper mode. We no longer support rule-based. We need to use the newer optimization style, and we should be optimizing for either all rows or first rows. And be very careful with hints. Okay? Hints are a way of getting the optimizer to do a particular aspect of an execution plan a certain way. And the reason why we call them hints, if I hint at something that's physically impossible for it to do, it will ignore me. Okay? If I tell it to use index 5 and somebody's already deleted index 5, it says, Trevor, nice try. I'm going to have to pick a different access path to do that execution plan. But they imply high maintenance. The problems with hints, and hints taken to extremes, are called outlines, which was a mechanism we used in the past to avoid changes when you upgraded the database. The problem with outlines and hints, it protects you from regressions, the behavior going negative. It also protects you from positive increases on the new version of Optimizer. So you should really test the code without the hints in it. So it implies a fair bit of maintenance overhead. I'm a big fan of hints to test on a test machine to try different execution plans. If I'm doing a really in-depth analysis and trying to figure out what's going on, I'm a big fan of not using them in production unless there's no other way of solving the problem. And with the SQL plan baseline, you can actually solve it without using hints. You can remove the hints later on. This is looking at doing a detailed tuning exercise, and we have a tool called the SQL Tuning Advisor, the little doctor in the middle. He's a specialist on tuning SQL statements. Okay, he'll go in and help you tune an SQL statement. It was originally designed as a DBA tool. It's now available to developers and SQL developer to help you tune new statements in your environment and your development machines. And it does all sorts of interesting checks. It will check that the optimizer statistics are appropriate for your tables and indexes, and they're not obsolete, and they look reasonable. It also checks the optimization mode the optimizer is running in, either all rows or first rows. All rows is the default on the database unless it's being changed by a DBA. And it's good for reporting systems, Oracle reports, etc. Data warehousing, data marts, etc. First rows is more appropriate for online applications or web-based applications. So fundamentally, we want to make sure we're optimizing the right way. Particularly on web-based applications, quite often the user gets some options that influences the SQL statement. They get some data back and they get some 10,000 rows and they scratch their head and say, let me refine my query. Things like searching Google on the web and Yahoo is very common. They execute SQL like that. So they refine their SQL to reduce the data, so quite often they don't run it to completion. In that case, first rows would be a better optimization technique for that application. It takes a look at the optimization mode. Okay. During the normal optimization process, we actually limit the optimizer to about a second to find a good execution plan. For some of Trevor's statements, that's much more time than we need. Okay, I do a select star from employees. A second is way more than the optimizer needs to figure out the right execution plan. No predicates. The only real option it has is to do a full table scan. Okay. For some complex statements that are joining many tables together with many complex subqueries, perhaps a second isn't enough time to look at all the execution plans. Perhaps it needs more time than that. So we can give it more time. How we give the optimizer more time today to find a better execution plan, because all it can honestly say during normal operation, within the second you gave me, I found what I believed was the best plan. It may not be, there may be a better plan out there if we give it more time. So use the SQL Tuning Advisor to give it more time. We can now give it minutes per statement instead of a second that we have. And then it may find a better execution plan. When you give it more time with the advisor and it finds a better execution, it can suggest a profile be created. It's an object in the data dictionary that allows the optimizer during normal optimization to include that better plan, and it still does the normal optimization. The purpose is over time, that better plan may not be the best plan into the future, and that your data may change, your environment may change, that maybe it's not the best plan, so we still let it optimize. It will also look at access paths. Do we have the index to support this particular query? If we're looking at a small subset of the data from a large table, an index access path is a better access path in a lot of cases in a full table scan. So it will suggest adding missing indexes. The only problem, it's got tunnel vision. It looks at one statement at a time when it looks at the statements. So one of the things we could do is have the DBAs run the Access Advisor. Usually it's only the DBAs that have access to it. But we can give it a group of statements that represents the workload on an application, and then it will look for optimizing the index across multiple SQL statements as part of the analysis. So it can be a good follow-on to using the SQL tuning device. Remember, it looks at one statement and only the indexes for one statement at a time. And it will look at the optimization mode. It will also look at simple structural changes that may improve the performance of the query. And we're going to look at these as part of the course later on. The next up is having a look at a parse time reduction strategy. Okay, and this is having our first look at the SQL results of a result of turning on SQL tracing and running tk-prof against it. And this is a partial dump from the tk-prof output. Okay, and in this we cut a lot of it. When we show it to you in the practice, you're going to realize there's a lot more to the tk-prof output. But we cut out the piece that we were really interested in. And we're going to look at this in more detail, but for you to understand what it tells you, I always review it a little bit. We're doing some sort of a select. We don't even show you the whole select statement. The tk-prof has the full SQL statement in it. Okay. We weren't really interested in the details of the SQL. And then we have a section that we have what we call a group of calls. When the database server processes the SQL statements, it looks at three aspects. It looks at a parse call that will go in and either build the initial execution plan into the shared memory in the SGA in the database, or it will look up an existing execution plan out of the shared pool. And we'll have a look at the details of this, but just to give you an overview. Then it looks at executing the statement. And then it looks at fetching. If it's a select statement, it uses all three of the calls: parse, execute, and fetch. If it's a DML statement, insert, update, delete, merge statement, it only uses the first two. Since this is a select, it's going to use all three of them. Okay, then we give you some information about each of those phases. The first thing we give you is a count. We parse the statement. In this case, we parsed it 5,500 times for 5,500 execution. For a well-written OLTP system, we would like to see it executed, parsed once, and executed many times. And when we look at the parse, we talk about a hard parse, which is the expensive one to build the execution plan for the statement, or we talk about a soft parse, where we have to look it up because my particular statement can't find it. Okay. Now, one of the things that could cause us to reparse it to do the soft parse particularly a lot, if I have a middle tier that is not using JDBC connection pools, or it's a .NET application that aren't using the .NET connection pools. If they're not using connection pools, then every time I go and execute a statement in the SQL application, it starts a dedicated server on the database server, and then it executes the one statement, and then it runs that dedicated server down. If we could reuse the dedicated server many times, we could actually have stored in the open cursors where they are. We could do a soft parse once to find it in the library cache in the shared pool of the SGA, and reuse that information many times. If we recreate a dedicated server each time, then we don't have the ability to do it. We have to do a soft parse even though it's a shareable statement. Another problem could be is we're not sharing the cursors, which could be caused because we're using literal values, not bind variables in an OLTP. The server sees, if we're using bind literals, it sees every SQL statement potentially as a different statement, and we have to hard parse it each time. That increases the cost of the parsing because we no longer do a soft parse every time, we have to do a hard parse. And we do 555 fetches. So there's something wrong, and these are the two things. Cursor sharing by not using literals, by using literals instead of bind variables. With bind variables, we see it as one statement. With one execution plan, many people can execute it, okay? Or by not using connection pooling. And we can tell how expensive each operation is. We give you CPU elapsed time, and this is expressed in seconds. The finest resolution is 100th of a second. So we're taking 100 seconds to do 555 parses. If we can reduce the number of parses, we can reduce the parse time. The execution is quite fast. It's less than half a second, technically 42/100ths of a second. And the fetches isn't too bad because we have to return the data. We also give you the elapsed time. I'm happy if they're in the same order of magnitude. If there takes 2 or 3 orders of magnitude more time to get the CPU time, to get the elapsed time, then I wonder why we're CPU bound, or are we wait state bound instead of CPU? It also summarizes the disk IOs, the number of blocks we have to look at in the database buffer cache. Okay, and we look at them in 2 modes. Query mode is used by queries. Current mode is generally used by DML statements. And then the number of rows. Well, note we're looking at over almost 1.5 million blocks in memory to return a total of 1,100 rows. That may indicate there's a better execution plan. Perhaps an index would allow us to go and access the data more efficiently.